Okay, let's talk about the difference between SQL and NoSQL databases. SQL databases, like MySQL or PostgreSQL, are based on a traditional spreadsheet-style model. Think tables, rows, and columns. They have a strict blueprint called a schema that you need to define upfront. And because of that structure, they're really good at ensuring data is reliable and consistent through something called ACID properties. Now, NoSQL databases are a different beast entirely. They don't force you into a rigid format. Instead, they are much more flexible, often storing data in documents or key-value pairs. This makes them great for things like handling unstructured data or when you need to scale your database really easily across multiple servers. Okay, let's talk about primary keys. They are absolutely crucial in database design. A primary key is essentially a way to uniquely identify each row in your table, like a unique ID card for every record. It guarantees that no two rows are exactly the same and helps maintain data integrity. They are super important for building relationships between tables too. You'll want to make sure it's unique, can't have any empty spots, no null values, and is often an integer for speed. Okay, let's talk about foreign keys. Essentially, a foreign key is like a little pointer connecting two different tables in your database. It's a column or sometimes a set of columns in one table that links back to the primary key in another table. Think of it as a reference, like a link saying this order belongs to this customer. It's crucial for making sure your data is consistent and accurate, preventing you from creating records that don't actually exist. For example, an orders table might have a customer ID column which acts as a foreign key, referencing the customer ID primary key in the customers table. This ensures every order is linked to a valid customer. Foreign keys are vital for data integrity, allowing you to maintain consistent relationships between your tables and ultimately helping you keep your database tidy and reliable. Okay, let's talk about joins in SQL. They are a really important part of combining data from different tables. We have four main types: inner joins, left joins, right joins, and full outer joins. An inner join only gives you rows where there's a match between the two tables based on your join condition. A left join keeps all the records from the left table. Even if there isn't a matching record in the right table, it fills in missing values with nulls. Then we have our right join, which does the opposite, keeping all records from the right table and filling in nulls from matched rows on the left. Finally, a full outer join combines every row from both tables, regardless of whether there's a match or not. Think of them as different ways to cover your data when merging information. Okay, let's talk about normalization, a really important concept when it comes to designing databases. Basically, it's all about organizing your data in a smart way to avoid repeating ourselves and keep everything consistent. Think of it like breaking down big tables into smaller, more focused ones. We use normal forms like 1NF, 2NF, and 3NF, which are guidelines that help us structure the data correctly. The goal is often to get to at least 3NF. Why bother? Well, normalization reduces redundancy, meaning we don't store the same information multiple times, saving space. It also ensures data integrity, so everything stays accurate when you update something. Plus, it makes updates and queries much easier and faster. Okay, let's talk about normal forms. Think of them like levels of organization for your data in a database. First normal form essentially says each column should hold just one piece of information, no repeating groups. Then we move to second normal form, which means if you have a combined key like an address, all the other columns need to depend on all asterisk parts of that key. Third normal form builds on that, making sure non-key attributes don't rely on each other indirectly through other non-key attributes. Finally, we have Boyce called normal form, which is strict. It ensures every determinant, which is basically a rule for choosing data, is itself a candidate key. Understanding these forms helps you design databases that are efficient and reliable. Okay, let's talk about denormalization, a really important concept in database design. Think of it like this: sometimes to speed up reading information from your database, you might intentionally duplicate some data that's frequently used together. It sounds counterintuitive, but by doing this, we can avoid having to perform complicated join operations which are slow. This is especially useful when you have a lot of queries pulling data from multiple tables. It dramatically improves how quickly those queries run. However, denormalization does come with trade-offs. It increases the amount of storage your database needs and makes updates a bit more involved, so it's crucial to consider whether it's truly necessary for your specific situation. Let's dive into indexes. They're a really important concept when we're talking about databases and performance. Imagine your database table is like a huge phone book. Finding one specific person without an index would take forever, right? An index is essentially the index at the back of that book. It's a separate data structure that lists all the values in certain columns and points directly to where those rows are located in the table. This way, when you run a search query, the database can use the index to quickly find exactly what you're looking for without having to scan every single row. It speeds up reads dramatically, making queries much faster, and it also helps with sorting and grouping data efficiently. However, keep in mind that adding an index does add a little overhead when you're writing data. Inserting, updating, or deleting rows requires the index to be updated too. Okay, let's talk about indexes. Think of them like the index at the back of a book. They help you quickly find what you're looking for in your database table. Indexes are essentially lookup tables that speed up data retrieval. There are several different types. You've got clustered indexes, which physically order the data on disk, non-clustered indexes, which create separate structures pointing to the actual data rows, composite indexes covering multiple columns, really important when you frequently filter by those together, unique indexes that ensure no duplicates exist in a column, and finally, full text indexes specifically for searching through large blocks of text. Choosing the right index type is key to optimizing your queries. Let's talk about composite keys. They're a really important concept in databases, especially when you're interviewing for SQL roles. Basically, a composite key is like having multiple clues to identify a specific record. Instead of relying on just one column to be unique, it's a combination of two or more columns working together. Think about student enrollment. A single student ID might not be enough. You also need to know which course they're taking. That's where a composite key comes in, using both the student ID and course ID. It helps maintain data integrity and is super useful when uniqueness can only be guaranteed by combining multiple attributes. Okay, let's talk about unique constraints. Essentially, they're rules you set in your database to make sure certain fields always contain different values. It prevents duplicate entries. Imagine trying to add two customers with the same email address. When we define a unique constraint on a column or set of columns, the database automatically checks for duplicates as you're inserting or updating data. For instance, if you create an email column in your employees table and apply a unique constraint, now two employees can have the same email. It's a really helpful way to maintain data integrity. Okay, let's talk about ACID. It's a really important concept in databases. Think of them as 4 key rules that guarantee your data is safe and reliable. First up is atomicity, which means if anything goes wrong during a transaction, the whole thing rolls back, nothing gets left in an inconsistent state. Then we have consistency, ensuring all rules and constraints are followed to keep things valid. Isolation guarantees that multiple transactions don't interfere with each other when they're running simultaneously. Finally, durability ensures that once a transaction is complete and saved, it stays that way even if the computer crashes. It's permanent. Okay, so let's talk about transactions. Basically, they're like a way to group multiple database operations together and treat them as one single action. Think of it as an all-or-nothing situation. Either everything in the transaction goes through successfully, or none of it does. It's really important that each step within a transaction is atomic, meaning it completes fully. The database needs to stay consistent too, so rules and constraints are always followed. Transactions also need to be isolated, which means they don't interfere with other things happening at the same time. And finally, they have to be durable, so once you've confirmed a transaction, those changes will stick around even if there's a power outage or something unexpected happens. Transactions are crucial for making sure your data is reliable and doesn't get messed up when multiple users are accessing it at the same time. Okay, let's talk about clustered and non-clustered indexes. They're super important for database performance. A clustered index is like a phone book. It physically sorts the data on your hard drive according to that index. Because of this physical sorting, you can only have one clustered index per table. Now, a non-clustered index is more like an index at the back of a book. It points you to where specific information is located in the table. You can have many of these. Think of it as a separate structure that helps the database quickly find rows based on certain columns. Understanding this difference will really help you optimize your queries. Okay, let's talk about stored procedures. Basically, they're like little programs you create inside your database. Instead of sending individual SQL commands over the network each time, you call a stored procedure, which is essentially a bunch of SQL statements bundled together, and it executes as one unit. This makes things much more efficient and reusable. You can use them to automate complex business logic, ensure data quality through validation rules, build reports quickly, or even control who has access to specific tables. It's all about making your database interactions cleaner and more secure. Okay, so let's talk about views versus regular tables in SQL. A view is really just a saved query. It's like taking a snapshot of the results of a specific SQL statement and storing that definition. It doesn't actually hold any data itself. Think of it as a shortcut. Now, a table, on the other hand, does store actual information directly on your database. You can insert new rows into a table, update existing ones, and delete them too. With a view, you can't do that directly. Any changes you make through a view are reflected in the underlying tables. Views also don't take up any physical space. They're just a logical construct based on what the query is returning. Okay, let's talk about how we remove data from a database using SQL. We have three main tools: delete, truncate, and drop. Delete is like carefully taking out specific people from a group. You need to tell it exactly who to remove with a condition. Truncate is like hitting reset on the entire table. It's super fast at clearing everything out, but doesn't track individual removals. And finally, drop is the most drastic. It completely gets rid of the table itself, so be really careful with that one. Okay, let's talk about subqueries. Think of them as many queries inside a larger query. Basically, they're questions nested within another question. You can use them in different places, like to filter results based on what another query returns. For example, we could find employees who make more than the average salary across the whole company. The code shows how that's done, using an inner query to get the average first and then comparing it with each employee's salary. Okay, let's talk about aggregate functions. Think of them as your SQL summarization tools. They aren't like regular select statements that give you one wrapper record. Aggregate functions take a whole group of rows and give you just one asterisk result for the entire group. Functions like count, sum, avg, min, and max are your friends here. Count tells you how many rows in a group exist. Sum adds up all the values. Avg calculates the average, and so on. We can use them with a group by clause to apply the aggregate function to each distinct group of data. Okay, let's talk about triggers. Essentially, they are like mini programs that automatically run within your database when certain actions happen. Think of it as a reaction. They can be activated by inserts, updates, or deletes on a particular table. They're super handy for making sure data is consistent and reliable, like enforcing rules you set up, logging changes, or even updating related tables without you having to write separate code for each operation. For example, if a customer's address changes, a trigger could automatically update the log of address history. Okay, let's talk about schemas. Imagine building a house. You need a blueprint, right? A database schema is essentially the same thing. It's like a detailed plan that describes exactly how your data will be organized within the database. It defines what tables you have. Think of them as individual containers for your information, like customers or products. Each table then has columns, which are the specific pieces of information you're storing about each item, things like customer ID, name, and email. The schema also specifies what type of data goes into each column. Is it a number? text, a date, and finally, it outlines how these tables relate to each other, often through links called foreign keys. A good schema makes sure your database is well structured and easy to work with. Okay, let's talk about a really common SQL interview question: the difference between where and having. Both are used for filtering data, but they work in completely different ways. The where clause filters * individual rows * before any calculations happen. It's like saying show me all employees with a salary over $50,000. The having clause, on the other hand, comes into play * after * you've grouped your data and calculated things like counts or averages. So it filters the * groups *, not the individual rows. Think of it as show me departments where the number of employees is greater than 2. The key takeaway is where filters rows, having filters groups. Let's look at a quick example in a table to illustrate how they work. Okay, let's talk about self-joins. They can seem a little tricky at first, but are super useful. Basically, you're joining a table to * itself *. Think of it as comparing rows within the same dataset. It's like saying find every employee and then find out who their manager is, all within the same query. You treat one instance of the table as the left side and another as the right side when you do the join. And crucially, you always need a common column to link those two instances together, like an employee ID linking an employee to their manager. Okay, so let's get into pagination in SQL. It's a really important skill for any database developer. Basically, we want to avoid showing users huge tables of data all at once. Pagination helps with that. It's like clicking next page on a website. We use the limit clause to restrict how many rows are returned by our query, and the offset clause tells SQL when to start returning those results, essentially skipping some rows. Think of it as jumping to a specific page number. But remember, you always need an order by clause to make sure your pages are in the correct order. And just a quick note, the way we implement offset might be slightly different depending on which database system you're using. Okay, let's talk about union and union all. They are both used to combine data from different queries, but they handle duplicate rows very differently. Union is like a filter, it only brings in the unique values, so if something appears twice in either of your original statements, you'll just see it once in the final combined result. On the other hand, union all is more straightforward. It takes * everything * from both queries and puts it all together, even if there are duplicates. Because of that, union all tends to be a bit quicker because it doesn't have to do extra work checking for and removing those duplicates. Let's talk about sharding. Imagine you have a massive database that's struggling to keep up with all the data and users. Sharding is like splitting that giant database into smaller, more manageable pieces. We call those pieces shards. It's really useful for scaling things up when your data gets huge or you're getting tons of traffic. Sharding can help improve performance by letting you run queries across multiple servers at once, and it even allows you to spread your database out geographically so users get faster access to the information they need. Okay, let's talk about materialized views. Think of them as a pre-calculated table based on the results of a complex SQL query. Unlike regular views, which just point to the underlying data and update dynamically, materialized views actually store the data themselves. It's like taking a snapshot in time. They are super helpful when you have really slow queries that you run repeatedly, especially for things like reports or dashboards where speed is key. They are fantastic for pre-calculating summaries too, like totals or averages. However, there's a catch. They take up storage space and need to be refreshed periodically to stay current, so you want to use them strategically when the benefits outweigh the maintenance cost. Okay, let's talk about referential integrity. Basically, it's a rule that keeps your database nice and tidy by making sure relationships between tables stay consistent. It does this through something called a foreign key. Think of it as a link connecting one table to another based on a common ID. Now, the really important part is what happens when you try to change or delete data in one of those tables. You have options like cascade, which means changes ripple through related tables, restrict, which prevents actions that would break the relationship, and no action, which simply blocks the action altogether. The goal is always to prevent invalid data from creeping into your database. It's all about ensuring accuracy and preventing errors. Okay, let's talk about deadlocks in SQL. They can be really tricky to debug. A deadlock happens when two or more transactions get stuck waiting for each other to release resources. It's like a traffic jam where everyone is blocked because no one is letting anyone else go. They usually happen when multiple transactions are trying to access the same tables at the same time, and they need to wait for each other to finish their work. To prevent them, you can make sure all transactions acquire locks in the same order. Keep your transactions as short as possible. Use timeouts so a transaction automatically rolls back if it's waiting too long, and avoid creating circular dependencies between tables. Basically, design your database carefully. Okay, let's talk about how databases handle simultaneous access. We have two main strategies for locking resources: pessimistic and optimistic locking. Pessimistic locking is like a physical lock. It assumes that conflicts will happen. So when you grab a resource, you get an exclusive lock on it, blocking everyone else until you're done. This prevents most problems, but can lead to deadlocks and reduce overall speed. On the other hand, optimistic locking is more relaxed. It assumes conflicts are rare. It checks if the data has changed before applying your update, so if something's been modified in the meantime, you have to retry. This allows for much higher concurrency, but you need a way to handle those potential conflicts. Okay, let's talk about correlated subqueries. They can seem a little tricky at first, but they're really useful. Basically, a correlated subquery is like giving your inner query access to information from the outer query. Think of it as each row in the outer query triggering a separate calculation using data from the same table. For instance, we might use one to find employees who earn more than average, or to filter results based on what another part of our database holds. The key is that the inner query's result depends on what's happening in the outer query. Each row gets its own mini calculation. It's a bit like having a helper inside your main query that uses information from the same table to make decisions. Okay, let's talk about OLTP and OLAP systems. They are both databases, but they serve very different purposes. Think of OLTP as the database you use for your daily operations like processing orders or handling bank transactions. It's built to quickly handle lots of small, individual requests. On the other hand, OLAP is geared towards analyzing past data and finding trends. It's all about business intelligence and reporting. OLTP uses a normalized structure which speeds up individual record access, while OLAP often utilizes denormalized schemas for faster analytical queries. Essentially, OLTP keeps things running smoothly in real time, and OLAP helps you understand why things are happening. Let's talk about something called data redundancy. Basically, having the same information stored multiple times within your database. It's not always a bad thing, but it can cause problems if you're not careful. Think of it like this: sometimes you need to store details in different places for efficiency or because older systems were built that way. But all that extra duplication can lead to higher storage costs and make keeping your data consistent a real challenge. Normalization is one key technique to combat this. Essentially, we rearrange our database structure to minimize those redundancies. There are also strategies like data warehousing and caching, which involve consolidating information or storing frequently used details in memory, but these need to be managed properly to avoid issues with outdated info. Okay, let's talk about backups. They're essential for safeguarding your data. There are a few different types of backups you can take: full, which copies the entire database; differential, which captures changes since the last full backup; and transaction log backups, which enable precise point-in-time recovery. You'll typically use tools like SQL Server Management Studio or TSQL commands to create these backups. Just remember to test your restoration process regularly to ensure everything works smoothly. Let's talk about char and varchar, two common data types for storing text in SQL databases. Char is like a fixed-size container. It always takes up the exact amount of space you declare, even if it's just a single letter or a space. Think of it as a precise box. On the other hand, varchar is more flexible. It only uses the space that's actually needed to hold your data. So, if you're storing names, which can vary in length, varchar will be much more efficient than char. It's all about how much space you want to allocate and whether the stored text lengths are consistent. Okay, let's talk about the group by clause. It's a really useful tool when you're working with SQL and analyzing data. Basically, it groups rows together that have the same value in one or more columns. Think of it like sorting your mail into different folders based on the sender. It pairs perfectly with aggregate functions like counting, summing, averaging, finding minimums or maximums so you can get a summary for each group. You can also use having to filter those groups after they've been created, which is really powerful. Okay, let's talk about how we deal with missing data in SQL specifically. What happens when a value is just absent? We represent this as null. Now, you can't use equal to or not equal to operators directly with null. They don't work the way you expect. Instead, you need to use is null and is not null. It's really important because if you accidentally try to compare a column with null using equals, it will always evaluate to false, even when the column actually asterisk is asterisk null. There are also some handy functions like coalesce. Think of this as a pick the first non-null function, and database-specific alternatives like fnull or nvl that can help you replace nulls with default values. When it comes to aggregate functions like counting rows or summing numbers, nulls are typically ignored. So, understanding how these different techniques work is key to getting accurate results in your queries. Okay, let's talk about cross-joins. Think of it as a way to create every possible pairing between rows in two different tables. It's like multiplying the number of rows in each table, so if you have 10 rows in one table and 5 in another, you'll get 50 rows back. It's not something you use all the time, but it comes up when you specifically need to generate every combination. For example, creating a report showing all possible combinations of products and customers. Okay, let's talk about data models. There are two main types, a logical and a physical. The logical model, think of it as a blueprint, describes what asterisk information you need to store and how those pieces relate to each other, like customers, orders, and their connections. It's all about the business requirements. Now, the physical model is what actually gets built. It's based on that logical plan, but it takes into account the specific database software using things like data types, how information is stored, and even indexes to speed up searches. Basically, the logical model tells you what asterisk to store, while the physical model explains how to do it. Okay, so let's dive into how transactions work when they're spread across different databases. It's a really interesting area, and it gets more complicated than you might think. The core problem is ensuring that if one database part fails, the whole transaction doesn't roll back read-atomicity, but across multiple systems. The traditional approach is called two-phase commit, or 2PC. Basically, there's a coordinator who asks each database and vault if it can complete its changes and then tells them all to either commit or abort. However, this method has some issues like blocking participants if the coordinator goes down, and it creates a single point of failure. Luckily, newer techniques using consensus algorithms like Graph or Paxos are becoming more popular. They use multiple nodes to agree on whether a transaction should succeed, which is much more resilient. Okay, let's talk about temporary tables in SQL. Think of them as little workspaces just for you during a single session with the database. They're different from regular tables. They don't take up permanent space and disappear when you close your connection. You often see them prefixed with a hash like hashtemp orders. They're super useful for storing intermediate results from complex queries, especially when you want to reuse those calculations in another query or simplify a multi-step process. If you find yourself repeating the same calculations over and over again in different parts of your SQL code, using a temporary table can really streamline things. For example, if you're calculating discounted prices as part of an order processing system, storing those calculated prices in a temporary table makes it much easier to join them with your order data. Okay, let's talk about cascading constraints. These are super useful when you have relationships between tables in your database. Basically, they tell SQL what to do automatically if you change or remove data in one table that's connected to another. There are two main types: on update cascade, which means if you update a value in the parent table, it updates related values in the child table too. And then there's on delete cascade, which is where things get interesting. If you delete something in the parent table, anything linked to it in the child table gets deleted automatically. It's important to think carefully about when and where to use these, because cascading deletes can have big impacts on your data. Okay, let's talk about CT. They stand for comment table expressions and are essentially like creating temporary tables inside your SQL queries. It's all defined using a with clause. You can think of them as named subqueries that make complex queries much easier to read and understand. They are super helpful because you can reuse the results of these temporary tables, making your code more modular and easier to maintain. In some cases, they can even help optimize performance. Let's dive into surrogate keys. These are basically fake, artificial primary keys we add to our tables. They are not based on any real data like a customer's email address or product code. Instead, they're just unique numbers that guarantee every record in the table can be identified without fail. Using them simplifies relationships and makes it easier to manage foreign keys, especially when your natural keys might change over time. Okay, let's talk about window functions. They are a really handy tool in SQL that can seem a little tricky at first. Basically, they allow you to perform calculations on groups of rows without actually grouping them together like you would with group by. Instead, they look at each row individually and compare it to other related rows, maybe the previous or next day's sales, for example. They use something called a frame, which tells SQL what rows to include in its calculations. You'll typically see this used with an order by clause to define how those windows are created. For instance, we might calculate a rolling average of sales over time. It can be a bit conceptual, but once you grasp the idea, they become incredibly useful for creating dynamic reports and insights. Okay, let's talk about tackling those frustrating slow queries. The first step is figuring out where the problem lies. Database monitoring tools and slow query logs are your friends here. Then, you need to understand how the database is executing your query. The explain plan command is super helpful for that. It shows you exactly what the database is doing behind the scenes. Look closely for things like full table scans, which can be a huge performance bottleneck. If you spot these issues, you can often fix them by adding indexes to relevant columns or rewriting your query to make it more efficient. Don't forget to test any changes you make always in a staging environment first. Got questions? Let's chat about it. Okay, let's talk about stored procedures. Essentially, they are like little programs inside your database, pre-written SQL code that you can reuse many times. One of the big wins is performance. Because they are compiled once and then executed repeatedly, they are faster than running equivalent queries directly. Security is also a plus. You can control access to data through the procedure itself. Plus, if you have several applications using similar database operations, stored procedures make sure everyone's doing things the same way. However, there are downsides too. They're often tied to a particular database system, which can make them less flexible. Debugging can be trickier than regular SQL queries, and changes need careful testing across all places that use them. Okay, let's talk about execution plans. They're super important for getting your SQL queries to run efficiently. Basically, an execution plan is like a step-by-step guide the database uses to find your data. It's not just guesswork. The DBMS builds this plan based on what it knows about your tables and indexes. When you analyze an execution plan, you're looking at how much work each step takes, things like scanning through a whole table versus using an index. You want to see low costs for everything. Pay attention to how tables are accessed, the join types being used, and whether indexes are actually being leveraged. A well-optimized execution plan can make a huge difference in query speed. Thank you for watching.